Hey, hi everybody. Today's plan is to go through a supplemental video on correlation and regression. And this video will be the last of the official supplemental videos for the course. There will be a couple of optional ones on some chi-squared tests and ANOVA. I don't know if I'll do that in one video or two, but those videos are optional and the associated homeworks are optional also. If you want to do the homeworks for bonus points, you can, or if you prefer to not deal with those videos during finals week and all of that, that's perfectly fine also. Okay, so what is the basic idea of correlation regression? The basic goal is to study the relationship between two variables, x and y, and specifically what we call the linear relationship between the two variables. So our inputs, our data, are ordered pairs, which we've seen before in the scatter plot graphical representation in chapter 2. So for example, a pretty kind of typical example is x is maybe height, and y is, say, weight of a person. So we have some data for heights and some data for weights. And importantly, this x is person one's height, and this y is person one's weight. And then person two, this x is person two's height, this y is person two's weight. So there's a natural pairing between each of these data points. So that's super important. These aren't just, I picked 100 random people and measured their heights, and then I picked a different 100 random people and measured their weights, and I have two lists. These are data that are kind of inherently paired. We could draw a scatter plot. And on a scatter plot, we could interpret this paired data as an x coordinate, comma, a y coordinate. In other words, a point in 2 dimensions. Maybe that's the height and weight for person 1. Maybe this is for person 2. This is for 3, and so on. And this might be a scatter plot. This might be, 10 or 15 people's paired heights and weights in a graphical representation. I could imagine I could have a scatter plot that looks, say, like this for a different scenario. I could have a scatter plot that looks maybe something like this, again, in a different scenario. So where the dots are just kind of somewhat uniformly distributed on this interval in x and y. And of course, our scatter plots don't always have to be in the first quadrant. X could be a variable that takes on some negative values, or y could be negative. I'm just drawing them in the first quadrant because it's a little easier to draw. Or I could have something like this. So here we're looking for a relationship between the two variables. Does a relationship seem to exist? In other words, what I mean by that is, if I know something about one of the variables, can I maybe make an inference about the other variable? Does that first knowledge, and somehow, loosely speaking, limit the reasonable possibilities for the second variable, right? In other words, if I know that somebody is very tall, I can probably infer that it's likely that they're heavier than average, or vice versa. So in other words, if I, just imagine restricting myself to, say, the right side of the x-axis here, I note that the y's that I tend to get over here tend to be kind of higher than average, right? The y results tend to be somewhere around here, and say not down there. Well, that looks like an X, but you get my point. Not here and tend to be more up here. So by knowing something about X, that tells me something about Y, at least tells me something probabilistically. So is there a relationship between X and Y here? It does seem so. What about over here? Again, if I pick, say, an X on, say, the higher side, I see that tends to be related to Y's that are on the lower side. So there does seem to be a relationship here as well, although the nature of the relationship might be a little different. If I move down, here I have this kind of curvy pattern here, but I can certainly say that if I have maybe an intermediate value of X, I tend to get a higher value of Y versus a very low or very high value of X tends to be associated with a lower value of Y. So if I know something about X, I seemingly can make an inference about Y here as well. So this might be something like speed that a car is driving versus fuel efficiency, miles per gallon, right? There's going to be some intermediate speed where you get pretty good mileage. But if you're sitting pretty much still, you're burning a lot of gas just to run the engine and you're not really going very far. So you don't get great mileage when you're going slow. And as you speed up, as you're going 70, 80 miles an hour or something on the highway, the air resistance starts to build up pretty quickly. Air resistance, roughly speaking, increases with the square of speed. So when you start going faster and faster, you get worse and worse mileage, even though you're moving a further distance, per second. You're burning more gas to overcome that air resistance, the rolling resistance from the tires heating up and all that kind of stuff. But if we look at the bottom left example here, I look at kind of for the overall X's, my overall Y's span about that much, right? If I, were to think about restricting myself to maybe higher values of X, well, the data still span kind of that same whole region in Y. Or if I thought about restricting myself to lower values of X, again, the data still kind of span the whole region in Y. In other words, if I know something about X, that doesn't really tell me anything about Y. If I know that X is higher or lower than typical or kind of in the middle, I don't know anything more about Y when knowing that about X than I did before I knew that about X. So there doesn't seem to be a relationship here. And this is related to, it's not exactly the same as, but this is related to the idea of independence. And kind of for our purposes, it's not too bad just to just say that, when we see something like this, we think of X and Y as independent. Remember in chapter 4, we had like the multiplication rule for dependent events versus independent events. Here, it's kind of like these two random variables are independent, that if I know something about one of them, that doesn't change what I know about the other one. Where, say, up here, if I know something about one of my variables, that somebody's, quite tall, that does change what I expect for the other variable. I expect to see a weight that's higher than average for that person. Okay, so that would be investigating the relationship between two variables. What do I mean by linear relationship? Well, if I imagine I come back over here and I say, all of these points, I might have 20 points here, or I might have 1,000 points, right? All these points, that's a lot of data. It's really hard for me to interpret. It's really hard for me to make heads or tails out of this, to make any inferences, to really gain an understanding of the phenomenon I'm studying, or anything deeper about the real world, looking at just all of this data. Can I come up with a model? Can I come up with kind of a simpler structure that can maybe tell me something about the thing that I'm studying, but that's not quite so data heavy as this data set. Now, back in chapter 3, we kind of did something like this a little bit. We might report X bar, right? We might report an average, and that's, I guess, in a loose sense, we can even think of that as a model. That's saying that, if I had to pick a number, if you told me pick a number, that if I had to set all of my data points equal to that number, maybe that would be the sensible number to set them to. Like if somebody made me do that, I might pick X bar. There are some maybe nice reasons to pick X bar. So it's kind of the typical data value in a sense. Well, we want to develop a model that's a little more complex here. We're interested in studying the relationship between X and Y, so I would like a model that relates these two variables to one another. There are tons and tons and tons of such models, but a pretty simple model is just a straight line. The good old y equals mx plus b, or in this case, I'm going to use slightly different letters. I'm going to use a plus bx, really for no other reason than those are the letters that are almost always used in this context. So here a is the intercept and b is the slope. So sorry about that, and mx plus b is kind of the intercept, but in the context of regression and correlation and statistics, b tends to be what we call the slope. So we have y equals a plus bx. This is a linear model. And as far as functions that relate x and y, a linear function is about as simple as you're going to get for a function that does actually vary, that does vary one of the variables when you change the other one. I suppose y equals a would be, the simplest model, something like that, but you don't see x popping up anywhere in there. That would be like our kind of, chapter 3 quote models, if we wanted to think of them that way. Okay, so I have y equals a plus bx, but this is a general formula for a line. If I have a particular data set, what line should I use? How should I choose a and b? So let's look at our height and weight data. And I think we can intuitively understand that, say, a line like this, a linear model like this, where I said for a given input x, my estimate for y is the y coordinate of that line, the associated y coordinate. I think we can see that this is probably not a very good model for this data, right? Why would we say that? When we say that doesn't look like a good model, what do we mean by that? Well, what I mean is that, oh, I drew dashed lines, so now I have to undo a whole bunch of times. What I mean by that is I can imagine this green line, this model, as really just consisting of a whole bunch of like theoretical data points, infinitely many like theoretical data points. And my blue data points are actual data points that came from the real world. And it doesn't seem like my blue data points tend to correspond very closely or very well to their green counterparts. In other words, if I look at this blue data point that has this x value, that data point has this y value, but my model would suggest this y value. That seems to be pretty far apart. And in fact, most of the data points seem to be pretty far away from the line. So that's probably not a super good line to pick as my model. And I drew a whole bunch of points, so let me just undo a whole bunch of times here. There we go. If I had a model like this, maybe for a different choice of a and b, here b would be positive, so I have a positive slope instead of the one I showed before would have a negative slope. I see that more of the points are pretty close to the line, but there still are some that are, pretty far away. Or if I choose a model, say like this, if I choose a model like that, well, now it really seems like a lot of the points are pretty close to this straight line. So this might be a choice of a and b for our, say, best linear model. maybe this choice of A and B that yields this line, maybe that's the one that we might find and say that that's our best linear model. In other words, it's the line that in some sense best models these data. I could do the same thing on the one over to the right. I could imagine drawing a line that is kind of the best model for that data, where the data points kind of are the closest in some sense, like on average, to that line. Now, if I look at the bottom left, well, I already said that I don't really think there's a relationship at all between X and Y. Do I think there's going to be a linear relationship? Well, a linear relationship is a subtype of a relationship, right? It's a specific type of relationship. If there's no relationship, I wouldn't expect there to be a linear relationship. And indeed, I can see that if, any line that I draw through these points, it seems to do a really terrible job of modeling them. It doesn't really capture what's, qualitatively going on at all. Even if I was careful and I kind of drew it, kind of nicely through the middle, it still doesn't seem to capture the qualitative phenomenon that's going on here. At least not like, the height and weight example or this other example, where the model does seem to capture at least a good bit of what's actually going on here. So here I might also say, this has a linear relationship and this does, because a straight line does a good job of modeling those data. But I might say that this one has no linear relationship. Again, it has kind of no relationship between the variables in the first place, so no linear relationship. And then lastly, let's look at this one on the bottom right, the speed versus miles per gallon. I'm going to blow this up a little bit just so you can see a little better. This one is a little tricky. It's a little nuanced, right? Because, well, we did see that there's a relationship. Pretty clearly, there's a relationship. Moderate speeds give you high gas mileage, and low or high speeds give you lower gas mileage. There's a relationship there. But is any line that I draw representative of this relationship? This relationship really looks like this. It's a very non-linear relationship. If I try to model this with a straight line, no straight line that I pick really does even a decent job of capturing what's going on here. Now, I can always find, the best linear model, whatever it may be. Maybe it's something like this. I don't know. I could say that's the best linear model. Maybe that's the one that is kind of closest on average to these data points. But that best linear model is really not a good model at all. So I would also say over here that there's no linear relationship. Now, being no linear relationship doesn't mean that there's no relationship between the variables at all. But if there's no relationship between the variables at all, that implies there is no linear relationship between them. So there are two ways that I can get an absence of a linear relationship. I could have no relationship at all. Then obviously there's no linear relationship. Or I could have a relationship that's quite non-linear like this. And here we also have no linear relationship. Now, keep in mind that that's not to say that, that every nonlinear relationship has no linear component to it. I could imagine data that are kind of like this, that I should have done a little better job of. But we can see that the general trend is kind of curving upward, but kind of only a little bit, right? In this scenario, I could actually imagine, even though the kind of true relationship might be nonlinear, I can imagine it not being so nonlinear that a line doesn't do a good job, right? This line does seem to do a pretty decent job of staying pretty close to most of the data. So maybe some linear relationship. This might be one that we would want to dig more into the numbers and analyze what we think the strength of that relationship is, and whether we think a linear model would be a good model to use or not. This might be a borderline case where we would want to investigate further. Okay. Okay, so that is the idea. We're studying the linear relationship between two variables. Now, related to this linear relationship, we have a couple of ideas. We have the correlation coefficient and we have the regression line. So the correlation coefficient, we could talk about the population correlation coefficient. In other words, if I had, say I had a whole population, all of Pittsburghers, and I measured the heights and weights of everybody in Pittsburgh, I could figure out the correlation for that XY set, and that would be a population parameter. Or I could take a sample and figure out the sample correlation coefficient. I could take a sample of size 100 and then maybe guess what the population parameter is on the basis of that sample, and that would be the sample correlation coefficient. In this lecture, we're just scratching the surface of correlation and regression. So I'm not really going to, delve too far into this. I probably won't be super careful about whether I call something R or rho, or whether I call it population or sample correlation coefficient. We're just scratching the surface. And as a general point, correlation and regression is a huge topic. It's a huge area. You could easily do, 2 semesters of study just in this area in intensive courses. You probably do a lot more than that. So we are really just scratching the surface of this topic. So the population correlation coefficient, rho, is the Greek letter R, which is why the letter R is the sample statistic. So this is rho. It's kind of like it looks a little bit like a P, but where a P kind of has a more straight tail, this is kind of has a curly tail. So this is a Greek small rho. And both the population and the sample correlation coefficient are in the interval -1 to 1, including the endpoints. And that's always true. That's from the way that they're calculated. They always have to be between -1 and 1. And these correlation coefficients have 2 characteristics. They have a magnitude, or an absolute value, between 0 and 1. And they have a sign, positive or negative. So let's investigate each of these individually. So magnitude between 0 and 1. So what does the size of the correlation coefficient tell us? What does the absolute value of the correlation coefficient tell us? It tells us the degree of the linear relationship between 2 variables, X and Y. If the magnitude is near 1, that indicates a high degree of a linear relationship. In other words, what that means is that I can find a line, a linear model, that is quite close to most of the data points. On the other hand, if it's near 0, that indicates a low, or maybe a completely absent, but a low degree of linear relationship between the 2 variables. In other words, even the best linear model I can find is not going to do a good job of modeling the data. It's going to be quite far away from most of the data points. So if I look over here, if I look at my top right example, that's maybe the kind of the best one, we can see that we found a line where almost all the data points are very, very close to that line. right? This tells me that I have a high magnitude for the correlation coefficient. It's going to be near 1 in magnitude. Or in other words, it's going to be near -1 or near +1. Similarly, for the top left, I see I found a line that does a really good job modeling the data, where most of the data points are pretty close to the line. This would also have a high magnitude. It would be near +1 or near -1. It would be near +1 in absolute value. It wouldn't be quite as high of magnitude as the top right, but it's really hard to estimate, would it be 0.7, 0.8, 0.9? Really hard to estimate like that, just looking at a scatter plot. But we can certainly say that we just looking at this, these linear models are doing a good job of approximating the data. They're doing a good job of modeling the data or the phenomenon that's going on. So we could confidently say there's a high magnitude of correlation here. Now, something like the bottom right, well, even the best line that I could find, if I tried a bunch of different lines, even the best one that I could find where the points tend to be the closest to that line, it's still a really bad model. So this would be a low magnitude of correlation. In other words, this would be near 0. So it might be a little bit negative or a little bit positive, but in either case, it's near 0. And same thing with over here. Any line that I was to try to use as a model, it does really a terrible job of modeling this data. So again, this would have a low magnitude of correlation. This would have a correlation near 0. Maybe a little positive, maybe a little negative, but it would be near 0. The other characteristic is the sign, positive or negative. If I have a reasonably high degree of a linear relationship, I might be interested in the nature of that relationship. Note that discussing the nature of the linear relationship is only really a sensible thing to discuss if we have a high degree of linear relationship, right? We can't talk about how the relationship works or what the relationship is like if there's not really a relationship to begin with. So the sign, positive or negative, is related to the nature of the linear relationship. So if, say, a moderate or high degree of relationship, then a positive sign on that correlation coefficient, so being, say, near +1, not near -1, but near +1, having a positive sign indicates a relationship in the positive direction, which isn't super helpful. But what do we mean by that? So we might say a positive relationship. And what we mean by that, let me get myself a little more room here. What I mean by that is high values of X related to high values of Y and vice versa. So it's positive in the sense that the two variables kind of move in the same direction, loosely speaking. It's positive in the sense that if I observe one variable and I see that it's higher than typical, my guess, my inference would be that the other variable is also higher than typical. And you can probably guess the negative sign, we would say that has a negative linear relationship. And in this case, the variables kind of move opposite. So higher than typical values of X tend to correspond to lower than typical values of Y. right? So if I know that one variable is higher than typical, I would guess that the other variable is lower than typical, and vice versa. So these are variables where there's maybe in some sense like a trade-off, we might think, if I have high value for one, I tend to have a lower value for the other and vice versa. So if I look over here, well, the bottom two that have no linear relationship, I'm not really interested in their sign because they don't really have a linear relationship to start with. But the top two, I can discuss the nature of their relationship. The top left, I see that higher values of x tend to be associated with higher values of y. Lower values of x tend to be associated with lower values of y. So this is a positive linear relationship. In other words, my correlation would be near +1. Maybe 0.7, maybe 0.8, maybe 0.9, but it would be a positive number that's kind of getting up near 1. On the other hand, top right, I see that higher values of x tend to be associated with lower values of y and vice versa. This is a negative linear relationship. In other words, my correlation would be something like close to -1. So maybe -0.7, -0.8, -0.9, something like that. Okay, so then moving on to the next idea that's closely related to correlation, that is regression. So for a regression line, the goal is to construct a linear model to model the relationship between x and y. So let's draw a scatter plot. And here I'll draw just a few points. We would normally want a data set with more points than this, but I'm just drawing a few so that the illustration's a little cleaner. And I would like to come up with a linear model for these points, right? I could think of a line like that seems to not do a great job. A line like that maybe that's a little bit better. But I think just visually we could see that a line, something like this might be a pretty good model. Why is this line a better model than those other ones? Well, because it tends to be closer to most of the data points. In other words, if I look at, let's just say, the vertical distance from each data point to this line, and that's a really tiny distance there, those distances kind of tend to be small, or at least smaller than other models that would be candidate models. So now what's the goal of my regression line? So here I have 5 points. These are my blue points here, my blue data. But what if I was interested in knowing, for this value of x, what do I think the value of y is? Well, if I look at this value of x, I don't have any data point that has x value of that value of this value here. There's no data point that's directly above that. So I can't just, look up the data point. Like I could say here, maybe my best guess would be this y value for this input x. But quite often I want to ask a question about a value of x that I don't have a data point for. Or maybe I could have 2 data points for the same value of x. And then if I'm asking about that value of x, which of the 2 should I go with? Well, this is one of the reasons we want to construct such linear models. It allows us to answer this question. We say we construct a linear model on the basis of the data. We pick our a and b, or our slope and intercept. We tune the model, we tune the line to be a good model. And then we can answer questions about the relationship on the basis of that model instead of directly trying to do it on the basis of the data. In other words, I could go up to my model and that's my y estimate. Well, I'm in blue now, but that's my y estimate. So for, this x, maybe this x is like 4. My estimate for y might be like, 17 or something like that. So I can do what's called interpolating. Interpolation. Or the other thing that I could maybe do is I could say, well, my x data kind of spans this chunk of my x-axis. Maybe I'll use blue again. What if I wanted to ask a question about an x that's, say, way out to the right? What if I wanted to know if my value for x for that variable was this number that's far out to the right, that's further to the right than any of the data that we have? What do I think the value for y would be? What would be my best guess? Well, here what I would do is I would just continue my linear model out. And again, I could use that model to answer this question. Right? This would be my guess for y. Because we've gone outside of the, in this case, the x data, we call this extrapolation. So that's why we might want such a model. Kind of as a side note, in general, interpolation is much more reliable than extrapolation. Because interpolation, we're kind of going in between data we already have, so things can't really get too crazy, right? There's no reason to say suspect that, these data points would be like up here when all the rest that are nearby inputs have a much lower value. But could I pretty reasonably expect that, if I go far enough to the right, that data points are going to start lying quite far off of this line? Sure. I mean, my data that I actually have observed don't really tell me much about this region way out to the right here at all. Okay. So how might I go about actually deciding what line I should use? What actual A and B, what actual intercept and slope should I use for this line to find my best line? Well, here's the general strategy. Let me erase a couple of things first. I want to get these bits off of here. I don't know why OneNote has this square and what you're actually erasing is like significantly bigger than the square. Let me just draw this back in a little bit here. Got a little carried away with my extra drawing on the chart here. Okay, so I had like this blue point, that one. Yeah, I think I had those 5. Okay. So now that we understand how we want to use our model and kind of what our model does, I can see that kind of run out of colors here. Maybe I'll just go back to black. I can see that, for instance, for this x, on one hand, maybe I'll call this, say, x1. On one hand, I have actual data point, x1, comma y1 over here. That's actual data that came from the real world. On the other hand, I have a model. If I have that y is a plus bx, then for x1, the height of this green line at x1 is a plus bx1. Now, my model in this case deviates from my actual experienced data by some amount, by actually this red amount here. So we have, for instance, error. We might call it epsilon1. Here, this is epsilon. It's the Greek letter E. It's the Greek E. And epsilon1 might be the difference between these two. Say yi minus a plus bxi. The actual observed value in the real world associated with xi versus the model's approximated value for yi at xi. Now we can see that if we change a and b, this error could get larger or smaller. I could imagine having error 2, which is like y2 minus a plus bx2, and so on down to error 5. So these are my 5 errors for these 5 data points corresponding to a model with a specific choice for A and a specific choice for B. Now I want to somehow kind of combine these into one kind of total error. But I do notice that, for instance, this error is going to be negative, but this one positive. If I kind of just add them up, I have that same problem back in chapter 3 whenever I was making the variance. When I add these up, there's a lot of cancellation. I don't want them to cancel. I want everything to come in the same direction. So I do what I did back in chapter 3. I'm instead going to look at the squared errors. And again, I see that as I change A and B, each of these errors squared is going to change. Then I can add them together. And when I add them together, I get what's called the SSE, the sum of squared errors. Note that SSE is a function of A and B. For different choices of intercept and slope, I end up with different sum of squared errors. When sum of squared errors is bigger, that means that my line tends to be further away from points, kind of on average or typically. And when sum of squared errors is smaller, that means my line tends to be kind of typically closer to the observed data. So how to find A and B? The intercept and slope of my linear model. Well, what I do is I choose A and B to minimize the sum of the squared errors. Now, in practice, coming up with formulas for A and B requires some calculus and things. So we're not going to go through that. The formulas for A and B, if you write them out kind of in longhand form, are kind of nasty. So we're also not going to compute A and B by hand. As kind of an aside, if any of you have some experience with linear algebra or anything, the formulas written in linear algebra form are actually very elegant and very simple. But if you try to write them out by hand in terms of all the xi's and yi's and all that, they're quite messy. So we're going to lean on Excel to do all the heavy lifting. I think this is all that I wanted to say for now on regression. And then there are two more, well, maybe one more point from these 2 quotes that I wanted to make. And that's that if we go back up here, what was our goal? To study the linear relationship between two variables. So we might be saying, well, this seems like kind of a silly problem, right? Well, this seems like a silly problem to solve. Essentially, everything in the world is nonlinear, right? There's this funny quote that dividing the world into linear versus nonlinear phenomena is like dividing all objects in the world into bananas and not bananas. In other words, like if you actually find a relationship that's really truly linear, like, that doesn't happen very often. So if just about everything we study is nonlinear, everything we're interested in is nonlinear, then why regression? Why are we interested in linear regression at all? Isn't this just useless? And the answer is no, it's actually incredibly useful. And there's two reasons for that. My favorite grad school professor, Professor Layton, he would love to say the world is locally linear. In other words, if I zoom out and I'm looking at the Earth from space, it looks very round. But if I zoom in a bit, it looks a little curvy. If I zoom in a bit more, it looks almost completely flat. So locally speaking, in other words, in some small region, we can approximate even a nonlinear function, even a highly nonlinear thing like a sphere, with a straight line or with a flat plane or something like that. So in other words, if I think back to my kind of speed limit in miles per gallon example, this is a very nonlinear phenomenon. I might want to use something like a quadratic or something to model this, but I don't really know how to do that yet. But maybe what I could say is, well, if I restrict my point of view to these x's, if I say I'm only interested in studying speeds that are less than 40 miles an hour or something, and I kind of get rid of this whole bit over here, well, now all of a sudden a linear model kind of does a pretty decent job, right? You might say like, well, maybe this is silly, but if I'm only interested in those speeds, if I'm designing some component of the car that's really only in operation at those speeds, like say some gear on a transmission or something, I don't know, maybe I don't care that much about the right hand side for that application. Somewhere where you see this fairly often is in medical testing. They might get data that looks like this, that is pretty nonlinear, say for some kind of growth curve for bacteria, something like that. And you might say, oh, this is really nonlinear, I don't want to model that with a line. But then they might look at a linear region, and they might say in that region, this data does pretty nicely conform to a straight line. Outside of that region, I'll just forget about that data. And essentially what this means is that if I measure whatever aspect of the patient sample that I'm measuring, if I measure it and it falls within this interval, I can report out a good report for my clinicians to use, maybe to develop a treatment or something like that. If it falls below that, we just say, well, sorry, this was out of the bounds of our test. Our test just isn't designed. It's not designed or validated or verified to test in these regions. That's just a limitation of the test. But maybe we could tell the clinician, they were above or below whatever, number that of interest. So that might be valuable information for the clinician. Maybe we can't give them kind of a quantitative result over here related to the quantitative input, but maybe we can give them a qualitative result. They were off to the right, they were off to the left of our validated region. And the second thing is, well, we're talking about a linear relationship between two variables, x and y. But I just called these x and y, right? If I imagine that I had, say, a list of heights, and a list of weights. And let me give, some heights, I don't know, in, let's say, inches or something, 60, 50, 55, 58. And I guess that's actually kind of short, but oh well, heights of kids. And weight, 100 pounds, 110, 80, 90. I don't know. Let's say these are kids. I don't know. And maybe I graph this. I look at the scatter plot and I say, oh, that's really nonlinear. So if I call this X and Y, I don't know if it's nonlinear or not, but let's just suppose it is. I'd say a linear model is no good there. Maybe it's kind of like this miles per gallon chart or something. If I called X height and Y weight, well, maybe I wouldn't be able to get a good linear model for that. But I could imagine that I could take these lists of numbers and make other lists based on them. Maybe something like weight squared, right? Or maybe like square root of weight. Or maybe like natural log of weight. If I call this X and this one Y, when I plot that, does that look kind of like a line? What about if I used this as the Y, right? What if I used, height minus 60 over, let's say over 3 or something like that. If I use this as X and this is Y. And this is actually kind of what a certain type of machine learning model does. Now, in that model, they actually have lots of variables they're trying to relate to one another, but they might have something like Y equals A plus B1X plus B2X squared plus B3X cubed. And they might even have cross terms. They might even have, plus B4XY or B5X squared Y cubed, or right. And you could imagine that in a big complicated model like this, where we could change all of these parameters, all of these A's and B's in a lot of different ways, we might be able to fit a very complicated curve, one much more complicated than this, very nicely using kind of an expanded idea of multiple regression with all of these different, different lists of numbers, X or X squared or Y squared or X times Y, or we could construct lots and lots of different lists of numbers combining these two lists in different ways and come up with new variables. We can do that a ton of times and then fit very complicated models by using just the machinery of linear regression. We can fit nonlinear models using linear regression. And that's the other really important piece here. Very important idea in machine learning algorithms and artificial intelligence and all of that. Okay, so hopefully that gives you the background of why linear regression is important, even though most of our problems are nonlinear. All right, so let's jump over to Excel now. Let me switch my screen share here. Okay, so jumping over to Excel now. Here I have some stock data. This is from about 10 years ago. I haven't redone this data because I actually grabbed a ton of stock data and went through it very carefully to find different pairings of variables that illustrated certain things that I wanted. So it took a lot of time to do that, and I probably should update it at some point, maybe after the next market crash or something. But so this data is a little bit old, but it still illustrates the point just fine. So what I have here is a list on certain dates spanning around 2 years, or around 1 year, sorry, from April 2012 to April 2013, of some stock prices. So for instance, this is Google's stock price on April 15th, 2013, Google stock price on April 8th that year, and so on. So this is essentially the price of Google per share, and this is basically the price of gold. It's not exactly, these are the prices for Spider's gold shares, which is an exchange traded fund. So you're not actually buying gold bullion, but you can essentially just think of this as like the price of maybe something like 1/10 of an ounce of gold or something like that. And we can plot these on a scatter plot because we see that they're naturally paired. This gold price and this Google price are both related to the date, April 15th, 2013. So I can plot on a scatter plot these two variables. So that's what my scatter plot looks like. And if I look at this scatter plot, it looks like there's really not much of a relationship at all here between gold and Google. And that's the first thing we're going to do. We're just going to look at these scatter plots for some different choices of variables and see whether we just kind of think there's a relationship or not. Gold and Microsoft's share price compared to the gold price is pretty much the same. It looks kind of just like a big blob. Doesn't seem to be much of a relationship at all. Google versus Microsoft, we're kind of getting closer, right? We're getting assets that we might start thinking are related to one another a little more. But again, if we look at the picture, it doesn't seem to be really a clear, discernible relationship for them. In other words, if I knew that Microsoft was, say, between 26 and 27, my estimate for Google is still pretty wide versus if it was 30 to 31, right? That's not super informative. Google versus Yahoo, getting into two search engines, we're getting a little closer now in the types of businesses these companies are in. And here we start to see something we can really see. It looks like a discernible relationship. It looks like if I knew that Yahoo's stock price was high, say 23, 24, 25, somewhere in there, I would estimate that Google's stock price would also be pretty high. And if I thought that Yahoo was low, let's say something like 17 or 18, let's kind of ignore this little left endpoint down here at 15, but say 17 or 18. In that case, I would guess that Google's price was a little lower than typical, 650 to 750 or something like that. And something like, here's an example of PIMCO's high yield bond fund. So these are bonds, these are corporate debt. So you might, buy a $1,000 bond from General Electric or something. And what that means is you're lending them $1,000 and they're going to pay you back some interest and then pay you that $1,000 back at the end of the term. And these are high yield bonds. So these are actually bonds that are in companies or from companies that are kind of in distress. They're not in the best financial shape. And we note that there kind of seems to be a bit of a positive relationship here as well between PIMCO and Microsoft. Maybe not as strong as the Google and Yahoo, maybe not as tightly clustered around a line, at least here on the right. But, there still seems to be a relationship. If I knew that that PIMCO was fairly high, say between 12 and 13, I might guess that Microsoft is probably a bit higher than average. And if I knew that PIMCO was low, say between 10 and 11, I might guess that Microsoft's price would be a bit lower than average. Now, any of you going into kind of finance or anything like that might find this a bit strange because typically bonds and stocks move opposite one another. So with bonds, you're kind of locking your money in at a certain rate for a certain period. And if your money is locked in at 6% and the stock market is doing really well, you'd probably rather have your money in the stock market. So that makes those bonds less attractive. And on the other side, if the market is crashing, that, guaranteed essentially 6% sounds really nice when the market is crashing. So typically stocks and bonds kind of move opposite directions of one another. But the important point here is that this is a high yield bond fund. These are companies that are in financial distress. So in tough economic conditions, those companies are probably also much more likely to go bankrupt. And in good economic conditions, those companies are less likely to go bankrupt. So these high yield bonds move a little more like stocks than like bonds. But so we see some relationship between these last two, but really not much relationship between the first three. Now, how do we compute the correlation coefficient in Excel? Well, we use the formula, built-in formula, COR-REL, correlation. So I do equals COR-REL, and then I pick array 1. So I pick my first list of numbers. Here I'll go with gold. And then comma, and array 2, my second list of numbers, Google. These have to be the same length, obviously, because it's expecting them to be paired. Close the parentheses. And there's my correlation. Oh, there's my correlation. Note that it doesn't matter which one you put first. If I put Google first and gold second, it would be the same calculation. So I see my correlation. It does have a negative sign, but note the magnitude, 0.01. That's about as close to 0 as you can get. This correlation near 0 in magnitude indicates a lack of a linear relationship between these two variables. All right, gold versus Microsoft. Here we have a correlation that in magnitude is about 8%, 0.08 on the scale from 0 to 1. So it does have a negative sign, but again, this is a pretty low number. This is probably indicating a lack of a linear relationship between these variables. I'm not all that interested in what sign it is. Microsoft versus Google, we're picking up some higher magnitude here for the correlation, about 0.3. So something like a third of the way up to 100%, third of the way from 0 to 1. But still, I would say that this is probably still a pretty low degree of relationship. But if we were going to say that there is some relationship here, we would guess that the nature of that relationship is negative. Now, Google and Yahoo, we see their correlation at about 0.8 on a scale from 0 to 1. That's a pretty high magnitude. So here I think that because of the higher magnitude, there does seem to be a linear component to the relationship between the variables. And now I'm interested in the sign. So it seems that that relationship has a positive nature, that when I observe higher values of one of the variables, I tend to also observe higher values of the other variable, and vice versa. And similarly with PIMCO and Microsoft, correlation of about 0.69, about 0.7. And again, I see that the magnitude of 0.7, that's getting up there, towards 1.0. So I think that there's a decent degree of relationship, of linear relationship between the two variables. And then I note the sign, because there is a relationship, I'm going to describe the nature of it. It has a positive sign. So this is a positive linear relationship between the variables. And again, that means observing a high value for one of them would lead me to the inference that I would expect to see a high value for the other one, and vice versa. Low, I would expect to correspond with low. So that's how to compute correlations on Excel. And there's one other thing that I want to point out, and I'm going to copy this over to OneNote, is that there sometimes, if you're just looking at a picture like this, sometimes it can be a little hard to discern. Do I think that there's a positive or negative relationship here? I'm not sure, maybe. Maybe it's a little hard to see just by eye. What I'll kind of do is I'll look at the blob of data and I'll pick something that's, kind of maybe what I might call the center. So maybe somewhere there, maybe somewhere, here. It's not like super important to get exactly the center or something like that, but kind of somewhere in this ballpark. And then I'll draw a vertical axis. And I'll draw a horizontal axis. Oh, missed it there. Draw a horizontal axis. Now, if I have my origin, the center, the intersection of my two axes, roughly in the middle of the data, both vertically and horizontally, if they have a positive relationship, so if the line slopes up, that means I'm going to have more data in the first and third quadrants and less in the second and fourth, right? If I see a lot of data in the first and third and not a lot in the second and fourth, that suggests a positive relationship. Or vice versa, if I see a lot in the second and fourth quadrants and not much in the first and third, that would suggest a negative relationship. So sometimes this can just be a little bit of a helpful trick to try to tease out if there's a bit of a relationship, right? Here with a correlation of only 0.7, it might be a little bit hard to see that positive relationship, or, maybe you can see it, pretty clearly just looking at it. But if you're having trouble kind of looking at these scatter plots and interpreting them, sometimes this can be a nice trick to use, especially on the ones that are a little less clear. Okay, so now what I would like to do is give you the opportunity to look at some scatter plots and try to match them with correlations. So here are 5 scatter plots with 5 correlations listed over here. And what I recommend you to do is just kind of pause the video, go through and try to match the scatter plot up with the correlation. Note that it would not be a fair question for me to say, point to a scatter plot, not give you, if I didn't give you this list, it wouldn't be fair for me to say, point to a scatter plot and say, what's the correlation, rounded to the nearest, 0.05 or something. That will be too difficult of a question to ask. Or it also wouldn't be really fair for me to say, draw me a picture that has a correlation of around 0.8. Again, that would be kind of too difficult of a question to ask. But if I give you these 5 plots and these 5 correlations, these correlations are sufficiently far apart that you should be able to tell which one is which plot, right? If this was like 0.96 and 0.97, and I had, the two are going to basically look the same, but 0.96 versus 0.8, those should look different enough, and the same with these. All right, so pause the video, try to match them up, and then we'll come right back. So coming back from our little break there, we have our 5 scatter plots and our 5 correlations. We can see that 2 of them are going to be positive, 2 negative, and 1 around 0. If I do that axes in the middle trick, kind of picking, say, a point in the middle of the data in the top left here, that might be something like y equals 10 and x equals 10, or x in the middle here, yeah, x equals 10, y equals 10, something like that. If I draw 2 axes there, I note that I have a lot of data in the top left and the bottom right, not much in the top right and bottom left. So that indicates a negative correlation. I note something similar for the bottom left scatter plot. Again, if I draw kind of a set of axes through something that's roughly the middle of the data, again, I see quadrants 2 and 4 have a lot of data points in them. Quadrants 1 and 3, not so much. Again, suggesting a negative relationship. I could say the similar but opposite for top center and bottom right. That these are going to have the positive relationship. If I draw, again, my axes kind of through the middle, I see a lot of data in quadrants 1 and 3, not much in quadrants 2 and 4, and similarly for bottom right. And then for the bottom center, I see if I draw, say, a vertical line around x equals 10 and a horizontal line maybe around y equals 10 as well, there seems to be a good bit of data in each of the 4 quadrants, maybe suggesting a low magnitude of the degree, or a low magnitude or a low degree of linear relationship between the 2 variables. Or another way of saying that is, if let's say that I knew that x was kind of higher than typical, say to the right of 10, that really wouldn't restrict the possible values for y at all. Or if I knew that x was to the left of 10, that also really wouldn't restrict where I'm likely to find y values. So I think that bottom center is going to be the correlation of 0. The two positive correlations are going to be top center and bottom right. The one with the higher magnitude. Now keep in mind, the magnitude of the correlation, it's not talking about the slope of the relationship. It's not talking about how much one variable seems to change when the other one does. It's talking about how strong the degree of linear relationship is. How tightly are these points clustered around a line? So this 0.96 is going to correspond with the bottom right scatter plot. These points are all clustered very tightly around the line, as opposed to say 0.8, this top center scatter plot where the points are clustered a little less close to a line. And then similarly with the negative correlations, the top left is going to have the correlation that's closer to -1, so higher in magnitude, but negative in sign. Bottom left is going to have the lower in magnitude, but negative in sign correlation. So top left is going to be my negative 0.98 correlation. Bottom left is my negative 0.74. Okay. Okay, and then the next topic that I want to discuss is actually computing regression lines on Excel. So the goal here is to use Excel to actually find, where was it? To actually find the A and B that minimize the sum of the squared errors, to actually find the intercept and the slope for that line. And here's an example that I have. So we're jumping right over to Google and Yahoo because we saw that they had what seemed like a high degree of linear relationship. So it makes sense to use a linear model to model this relationship, right? That was the correlation of 0.79. So if I have Excel do the number crunching, what it tells me is that this is the slope and intercept I should use. The slope should be 21.6, the intercept 304. Or in other words, I estimate that Google stock price is, what was it, 304 and 21.6. So 304 plus 21.6 times Yahoo stock price. So if you give me a hypothetical Yahoo stock price, $10, then I would estimate Google to be 304 plus 21.6 times 10, or 304 plus 216. What's that, like 520, something like that. So I got this red line on here just by making a new column, Google estimate, and it is just the slope, or sorry, the intercept 304. That's H23 plus the slope plus H22 times the Yahoo price. So for each of the data points, I'm just choosing to compute the Google estimate. I have the actual real world value and I have the estimate from my model, and I see there's a deviation there, right? I'm about, looks like 11 or so units off for this particular data point. When Yahoo was 23.47, we saw a Google price of $799.87, and our estimate would have been 811.31. So we were off a little bit. We can compute these estimates for each of the Yahoo prices going along here. And then we could imagine that we could take this difference, square it, that would get us an error. And we could add all of the squared errors together, that would get us a sum of squared errors. And Excel is claiming that choosing this slope and this intercept yields the lowest sum of squared errors. That no other line with a different slope and intercept would yield a lower sum of squared errors. Now, how do I actually compute this? How do I actually get Excel to do this for me? Well, what I do is I go up here to data and I go to the data analysis tab. We added this in already. You have to add it in if you haven't already done it, but I think have done it previously in class. But I will show you really quickly how to add it in, just in case you're using a different version or a different computer or something. So you go to File, Options, Add-ins. Down here where it says Manage Excel Add-ins, hit Go. And then just make sure that Analysis Toolpack is checked. Check it, hit OK. You should see it pop up here under the Data tab, Data Analysis. And this is where we can do things like, say, compute descriptive statistics or make histograms, but we can also do regression. So that's what we'll choose, regression. And it's asking me to input a Y range. So that's my Y variable. I'm going to use labels. So that way, instead of just calling it like X and Y or something like that, or variable 1 and variable 2, it'll use the names that I've given up here. So the Y range, the Y variable is going to be Google, and I'm going to include the label. So I'll just click all the way at the top and then shift and click at the bottom. That enters my Y range. My X range, my independent variable, will be Yahoo. And maybe I'll do residual plots here. Okay. And the rest of these check marks I'll leave unchecked. And I see that this outputs a new spreadsheet, worksheet ply. So here's my Google Yahoo data. And on the basis of this data, I see a few things. These are the things I'm going to be interested in. This thing here that says multiple R, as well as R squared. And I'm going to be interested in, for the coefficient of Yahoo, for the slope, the p-value. So I'll just put a couple asterisks there, here, and there. So these are the things I'm going to be interested in. So this thing that they call multiple R, that's the correlation coefficient. They call it multiple R because the calculation here could be a little more general than what we're doing. Like I said, there's lots of other applications of regression, but for our purposes, if we're just doing one input variable, one output variable, and that's it, then multiple R is just the correlation coefficient. So that's that 0.79. Remember, that's the number that we computed just with a CR-REL function, this 0.79 number. R squared is literally the correlation squared. So if I do equals this number to the second power, you see I get that number. Again, wanted to delete this one. Again, there are things like the adjusted R squared here and so on. They come into play for other applications of regression that we're not getting into. But one important point here with R squared, this gets a certain name. It's called the coefficient of determination. And it's essentially the explanatory power of the linear model. R squared is the proportion of variation in variable y explained essentially by the model, or really by variations in x. In other words, here we see R squared of about 63%. So what this tells us is that I can explain about 63% of the fluctuations in Google stock price using a linear model based on Yahoo stock price. And there's something like 37% of the variations in Google stock price that I can't explain from this model. So having a high R squared is good. So we want this to be high, right? If I have a model where one variable only explains 1% of what's going on in the other variable, that's not a very useful model. Now, like, what's high enough that I'm happy with it? Well, that's probably going to be dependent on context and what field I'm working in and the complexity of the problem and so on, right? So, maybe there are some fields that are really happy to get 20 or 30% explanatory power for a really complex process that's very poorly understood at this point. And there are other fields that might want an 80% explanatory power. But we want generally the R squared to be high. Higher is better than lower. And then the other thing we see is that if we have a p-value down here. So what is that p-value for? Well, that obviously indicates there's a hypothesis test going on. And here's the idea. We have a model. This is based on a sample. Y equals a plus bx. We figured out a and b based on sample data. In other words, these a and b, or in other words, this 304 and 21 are sample statistics. Well, in reality, if we had access to the entire population, we wouldn't have to estimate A and B. We could compute what we might call alpha and beta. This isn't the same alpha and beta as, like in hypothesis testing before, where we had alpha was a significance level. This is a different alpha and beta. So sorry about that. When you jump into regression, kind of, most of the variables kind of reset and mean different things. So sorry about that. But these are population parameters. In other words, if I had access to the whole population, I could do the same process for linear regression and know what alpha and beta were for the whole population. A and B are estimators of alpha and beta. My hypotheses that I'm talking about here are about beta. On the basis of this sample information, do I think that beta is 0 or do I think that beta is non-zero? So the p-value for the slope, this is the slope variable, the one that multiplies Yahoo. The p-value for the slope is related to this hypothesis test. Beta equals 0 just means like y equals alpha, like my best guess at y doesn't depend on x at all. So this is no linear relationship. If I am going to move forward under the hypothesis that my variables don't have any linear relationship, does it make sense to make use of a linear model? Probably not, right? I would probably want to trash that model if I thought that there wasn't a linear relationship. If I was going to move forward on the hypothesis that beta is 0, that there's no linear relationship between x and y. If I can reject the null in favor of the alternative, I can conclude that beta is non-zero, and I can move forward under the presumption that beta is non-zero and that there is an actual linear component to the relationship between x and y. And then a linear model is probably a reasonable model to use, again, provided we have a decent explanatory power. So can we reject H0 in favor of H1? Well, maybe if P is less than, say, 5%. For instance, that would probably be a fairly typical one to use. Usually we don't have to really worry about 1, 5, or 10%. We typically get p-values that are like this. The p-value here, this E means times 10 to the power. So our p-value, 1.5 times 10 to the minus 12. 1 in a trillion, that's significant at the 10, 5, or 1% level, right? Much, much less than 1%. So this would be significant. And we would reject the null in favor of the alternative. We would conclude that there is a linear component to the relationship between Google and Yahoo stock prices. When we get a result that's not significant, quite often our p-value is like 20% or 30% or something. It's quite often obviously not significant. Okay, so the Google Yahoo is a good model. We can see that looking at the picture. The picture of the model seems to do a pretty good job of modeling the data. We can see that it has an R squared of 63% or so. It's explaining about 2/3 of what's going on. That's probably pretty good. And a p-value that's highly significant. So we'd be quite happy using this model. There's a couple other things in here that I'm not going to talk about. I'll just really briefly mention that if instead of looking at the data X and Y, if I standardize the data, X minus the mean of X, let's say X bar, the mean of X over the standard deviation of X, and Y minus mean of Y over standard deviation of Y. If I standardized each of these points and I looked at these standardized variables, maybe we can call this like Z and W. The first thing is that for Z and W, the regression line goes through 0, 0. So the intercept A is 0. And the second thing is that the slope B is the correlation. So if you standardize your variables first, the first thing you do is you demean them. You subtract off the mean, which is what pulls that center of the data back to 0, 0 and makes the intercept 0. And by dividing by the standard deviations, you make the slope of the regression line the correlation. So there are some other, if we had more time, we might go into that a little deeper, but I'm just going to leave it at that. So let's look at the result for PIMCO and Microsoft. Again, we saw that this had a correlation of 70%, right? The explanatory power, the R squared, is going to be something like 50%. That seems like a decent number to a decent explanatory power. We're explaining half of what's going on. So it seems sensible to construct a linear model here. So again, I'll go to data analysis, regression, and 1 to 54 is at, I think because I entered it before for Google and Yahoo, it is still in there. It looks like it is. That all looks good. And let me zoom in a little bit, clean this up a bit. So again, I see my R squared of 48%. So this model is explaining about 48% of what's going on with Microsoft using PIMCO. My correlation of about 70%. And my p-value for the slope down here, 10 to the minus 9. So about 1 in a billion. Certainly less than 1%. we could quite confidently reject the null in favor of the alternative and conclude there is a linear relationship between the variables. So it's sensible to use a linear model. So the things I want to check are low p-value, high r squared, and then just kind of a sensibility check, right? I just look at the model and say, does the model seem to do a good job of interpreting the data? Seems to be pretty good. Now, there is something that I might notice here is that pretty consistently from the left to the right side, the data points are pretty consistently, maybe with the exception of these couple up here, but they're a pretty consistent distance away from the line. Or in other words, my errors, that kind of chose a funky, trying to expand this a little bit. There we go. It kind of chose a funky x-axis to plot these on, but my errors or my residuals are kind of, evenly distributed across from between 10 and 14. They seem to be kind of evenly distributed up and down as well. So they seem to be kind of randomly scattered about. If I go back to my Google Yahoo example and I look at my residuals, let me expand this out a little bit. I noticed that to the right here, it seems like there's a certain variability, but over here to the left near 15, it seems like there's a lot more variability. And I actually see that in my picture also. I see that my model does a really good job from maybe something like 16 or 17 on up to 25 for the Yahoo price. But down here near Yahoo 15, my model does kind of a terrible job. Google is just all over the place when Yahoo is 15 or near 15. So this is something called heteroskedasticity. It's a big, long way of saying that there's unequal variance across the different ranges of inputs. And that's actually quite a problem. So there are similar, there are other problems that can come up in regressions that we would want to look for, and that if we saw, we would want to correct. And again, this is where, like I said, there's all that extra study that can go into this. This is where all of that comes in, right? Is knowing what to look for, what problems can occur, and then maybe how to correct them if they do occur. So we're certainly not getting into that, but just know that there's a lot that, to use these models really properly, there's a lot that should be looked at. Okay, so now let's look at Google versus Gold. So this had a correlation of like 0.01. So we had said before, I don't know why it's doing this, but we had said before that it doesn't really seem like this is, it doesn't really seem like there's really a linear relationship here at all. If we force the issue, if we say, okay, give me the best linear model, well, Excel will give me a best linear model, but it might be a terrible linear model. And in this case, just looking at the picture, we can see that the linear model doesn't look like it does a good job of modeling the data at all. But it's important to realize that if you say, give me the best linear model, you'll get a best linear model, but it might not be a good one. How would we know it's not a good one? Well, one thing is just look at the picture. But what are the numbers going to look like? I have an r square of about as close to 0 as you can get. 2 times 10 to the minus 4. That's a very low r squared. Very low explanatory power. This model is essentially explaining nothing about the price of Google's share price using gold. The other thing is our p-value. Remember, we're looking for low p-values. We're looking for p-values that are like less than 5% or less than 1%. Our p-value is 92%. It's not 0.92%, it's 92%. That's an enormous p-value, right? We're looking for p-values like 5%, 3%, 1%, or smaller, and we get a p-value of 92%. We definitely cannot conclude that there's a linear relationship between the variables. Okay. So this would be, the first example was an example of a very nice regression. The second one, maybe a moderate. this would be a very terrible regression outcome. And then one last thing that I just want to point out super quickly here is if I take the S&P 500, and here I'm cheating a little bit, I'm kind of using time as the independent variable and price as the dependent. So here we have something that's like a time series. We see we have the crash, the housing market crash, and a recovery. I have a correlation of 0.42. And if I look at my regression output, I get an R squared of 18% and a p-value that's pretty significant, 3 times 10 to the minus 4. So I have 18% explanatory power. Right. But if I choose a different era, a different time period, all of a sudden I have a correlation of 93% and 87% explanatory power. So when I'm dealing with time series, or when I'm dealing with kind of a data set where I can kind of choose the cutoffs or choose in a sense what data to use, it's very important to be aware of the fact that data could be chosen in such a way to make a result look better or worse, right? This looks like an awesome regression result. This looks like a okay, but not too great one. The other thing to realize is that in time series, which really all of these are, but this is particularly obvious, you look at our errors here, there's a very clear pattern to our errors. They start high, they go low, and then they increase again. Typically, that's an indication of a problem with the regression, that one of the assumptions really wasn't satisfied. And we even see something a little similar here. We see these kind of patterns in the residuals. Not quite as bad, but we do kind of see them. So there are a lot of things in these regressions to look for, especially when it comes to anything involving time. So even these stock prices that didn't have time like as an explicit input, even these ones like over here, where I just had, 2 share prices that were related to one another, they were implicitly related through time. Anytime we're in time series, that adds a whole other layer of complexity, and that, that's like another semester or 2 of study that you could do on top of regression to look at how to analyze and correct for all of that stuff. So this is a huge field, an enormous field, but hopefully I've given you some appreciation for it and some understanding of the basic ideas. And there's one last thing that I want to do is I want to just really quickly go through and make sure that I hit all the high points, because this is kind of a crash course. So, just a few last thoughts on hypothesis tests. If you're interested, you can read through these. I won't, we're already kind of late on time, so I won't talk much more. But scatter plots and correlation, I think we hit all of these topics. And just a reminder from all the way back in chapter 1, correlation does not imply causation, or a strong regression result does not imply causation. Just showing that the two are related, that there's a strong degree of relationship, doesn't tell you that one causes the other, or that it doesn't tell you which way the causation is, or even that one causes the other. It could be a third variable causing both or something like that. We talked about that. I talked about how using standardized variables can make the calculation simpler and a little easier to understand. It also gets rid of units, which is another plus, but that's something that's really secondary, of secondary importance. Okay, and I think that was, yeah. So I guess the summarization here is fairly important. What makes a good linear model? First, look at the model in relation to the scatter plot and just make sure it kind of looks reasonable. Does it seem like it does a good job of modeling the data? We're looking for a low p-value for the slope. We're looking for a high R squared, so high explanatory power of the model. And something that we didn't really talk about, but that if we're going to go further with this, that we would talk a lot about, is there are modeling assumptions. So what should the residuals look like? The residuals should be kind of random. The errors should be kind of random. They shouldn't follow a pattern like we saw in some of them. We should have homoscedasticity. We should have the errors shouldn't be like really variable on one side and less variable on the other side. They should be kind of the same variability all the way across. And one of the problems is that even folks who are doing this for research and things like that, research papers, I mean, not statisticians doing research, but folks using linear regression as part of biology research or something, if they're doing their own stats, a lot of times they don't really check these assumptions. And there are some important modeling assumptions underlying these techniques. So it is important to check those. We didn't get into that. Again, this is a huge topic, but at the very least, I want you to appreciate that it is a huge topic and that it should be taken with care. And when you see somebody present a linear model, just remember that it's a complex thing that is going on behind the scenes they're presenting, even though the end result model looks fairly simple. Okay, so I think that wraps up our discussion of correlation and regression. And that really wraps up the material for the course. So again, keep an eye out for the extra optional supplements, but this wraps up the material for the course and for the final exam.